Hello and welcome to another day of Advent of Code. We are back for day 22, which is, oh boy, another three-dimensional space problem, which is a bit of a mind bender. All right, so for day 22, if we take a look at, I'm just going to show you code for this one since the code is a little bit involved. But if we look at our input, we're going to have a series of on and off cubes. They're represented with either an on or an off in the first part, and then ranges. Note that these ranges are inclusive, so this cube, even though it's 20 to 26, is actually 7 wide, which makes some of the math a little bit fiddly. And part 1 asks us to run all of these toggles. So these toggles are setting points in space to either be on or off. And it says to ignore any points which are less than -50 or greater than 50. So for instance, this doesn't cover anything in that range, and so it would get completely ignored, as would this one here as well. So in this particular example, we're only going to consider those ones. And just run all of those. And at the end, you note how many points are set. And so for part 1, I just brute forced this. I didn't really put too much thought to it. I guess we can look at our parsing first. For the parsing, I basically just parsed the X, Y, and Z and a Boolean as to whether they were on. Some pretty straightforward splitting the strings apart, chopping off the X equals Y equals on the beginning, and then checking if the thing is on for our Boolean here. As for the computation, I basically kept a set of points and generated all the points for each step. Note here that I am using range and +1 because they're inclusive, so we need to make sure that we include the end. I'm also using max and min to clamp it between -50 and 50. And then if it's on, we're ORing with the set, so we're unioning the two values. And if it's off, we're subtracting those points from the set. So we're doing a disjoint operation. So that's how I add the points to this coordinate set, and then at the end we just have the length of that, which is pretty slow, but it gets the job done for part 1 because we only have to consider this. However, in the back of my head, I was thinking, oh no, part 2 is definitely going to be, ignore these bounds and actually do the clever math for this. And so the way that I approached part 2 was to consider the cubes as their own data structure. So I built a cube data structure which has the x's and y's for each of those. And I changed it to be not inclusive, which made the math a lot easier for some of the stuff, particularly the size and the cube splitting, which I'll get to in a second. We're going to skip over that really quickly. But basically, I represented the current state as a list of cubes, and then for each step, I either subtracted from the cubes by chunking them up into a bunch of different chunks, or yeah, I basically just did that. So in fact, I represented my addition as subtracting from the current cubes and then just adding the whole cube at the end. So for normal subtraction, it looks like this. Basically, loop over every existing cube and subtract from it. This either, if it doesn't intersect, just returns back the original cube, or it splits up the cube if it needs to. Or if it completely destroys the cube just goes away. And so that's all bundled into the complexity of this subtract function. But other than that, this reads pretty straightforward. And at the end, we just sum the sizes of the cubes. So let me show you how I kind of thought about this. So, or at least how I thought about the intersection. So when we're intersecting cubes, we kind of have two cubes, and they might overlap in a particular way. They might, not overlap in a particular way. But let's consider the, the blue cube here to be one of the two cubes that's overlapping. So what I actually did is I took all 4 of the coordinates that are involved here. So the edge of this cube, I guess there's 4 here. So this cube edge, and this cube edge. Let's imagine that this cube actually extends further out in both of these directions. So there's a 4th edge here as well, or 4th point on each axis. And so then I have 4 points in each axis, and they might represent parts of this cube, they might represent parts of this cube, but I didn't really want to think about them. I just knew that there were 4 points in each dimension, so we have a larger cube like this. And when you have a larger cube, you basically segment into each of the different 27 possibilities here, and if you find the ones that are in the one cube but not in the other, that allows you to do the subtraction. So you can imagine here, the blue ones are the ones that we subtract out, and so we're left with all the other ones in this particular case. It's also possible that your cube is entirely contained, on an edge of this, and so this might be the only cube that gets subtracted out or something like that. But that's kind of how I thought about it. But let me show you the code for it because it's a little bit fiddly. Yeah, so these are the methods that I needed. So I had size, which is just the difference of each edge multiplied together because they're not cubes. I realize I used the word cube. They're not cubes. They're rectangular prisms, but pedantics. I have an intersection function. This I actually wrote before I refactored to be non-inclusive, so that's why it has these -1s and less than or equal tos. It really could just be less than and without changing this here. But this made it a little bit easier for me to think about it. I have a contains function for completely enveloping another cube. We use that later. And then I have a subtraction. So I talked about those 4 points earlier. Those 4 points are basically the 4 x coordinates, or the 4 axis coordinates on that particular axis, 2 from the current cube. I'm going to call them cubes even though they're actually rectangular prisms, and 2 from the other cube. And I didn't really want to think about it, but if you sort these, you end up with 4 points on a line, or sometimes you end up with fewer points on a line. You can have empty cubes, which I didn't actually eliminate. So there's there's potentially empty cubes that chill around, but they will always have a size of 0, so it doesn't actually matter. But yeah, sort those 4, and then you end up with all of the points in each of these axes. So you can imagine, you have point 1, 2, 3, and 4 in that axis, and you would have points 1, 2, 3, 4 in this axis, and then if you had your, what's the other axis? This direction. You would have 1, 2, 3, 4 in this direction, and from that you can generate 27 different cubes. And that's what this diagram kind of represents. Once you've generated those 27 cubes, you can figure out whether they participate or don't participate in the subtraction by seeing if the current cube contains it and the other cube intersects with it. So we should keep things that are inside of our cube and get rid of things that intersect with the other cube, basically. And so this is how I did my subtraction. And then I basically just use this subtraction to do all of the state here. So every operation is represented as a subtraction and then an append, basically, if it needs to do turn them on. Because I didn't want to double count, so I subtracted out all the intersections, and then you just add in the remaining cube. But yeah, this worked fairly well, and it's actually pretty fast too. I mean, pretty fast. It's Python, so it's kind of slow, but this computes it in a 1.5 seconds, which is pretty reasonable. I heard of a bunch of other kind of cool solutions to this. One of them, I'll just describe one of them because I didn't actually implement it. One idea is that there are a fixed number of coordinates in the input. So you can imagine all these inputs here. And so what you can do is kind of draw cubes for each possible thing and then color, uncolor based on those. So instead of, we were originally drawing one individual dot at a time. So instead of drawing individual dots, you draw individual cubes, basically splitting the input space based on all of these potential coordinates. And so that makes the math a lot better, but doesn't mean, it means you don't have to worry about all the cube math and intersection and all that other stuff. And I heard of a couple other solutions, but those are the only ones I remember. Anyway, hopefully you found this interesting, and I will see you around for the next day.